Imagine the vast expanse of our universe, the galaxies stretching out beyond our wildest imagination, stars born in nebulae, some of them living out their lives in spectacular explosions, others quietly burning for billions of years. And scattered throughout this expansive universe, we have black holes, these enigmatic entities that not only defy our conventional understanding of physics but also challenge the very fabric of spacetime itself. Black holes are typically seen as places where gravity is so intense that nothing, no matter, no light, and no signal, can escape their grasp. They're the cosmic monsters that seem to suck everything in, yet we can never get close enough to witness their inner workings firsthand. It's in these black holes, however, that we also encounter one of the most mysterious and paradoxical ideas in modern physics, the concept of the singularity. Now, here's the thing that might blow your mind. What if this singularity that we've come to accept as the ultimate endpoint in space and time doesn't actually exist? What if our understanding of black holes, and even the beginning of the universe itself, could be built on a mistaken foundation? Could it be that singularities, those theoretical points where spacetime is warped beyond recognition, don't exist at all? This is exactly the question posed by Roy Kerr, a renowned physicist and mathematician whose work on rotating black holes has had a profound impact on our understanding of the cosmos. Kerr's groundbreaking theory challenges the existence of singularities, and if proven correct, it would upend much of what we think we know about spacetime, gravity, and the very nature of the universe. So, what if the universe didn't start with a Big Bang centered around a singularity? What if black holes are not the death traps of the universe, but something entirely different? These are not the musings of a fringe theorist but the serious ideas of a scientist with decades of expertise in the field. To fully grasp what Kerr's ideas entail, we need to first understand where the concept of the singularity originated and why it has been so central to our understanding of black holes and the universe. The theory of the singularity is deeply rooted in Albert Einstein's general theory of relativity. When Einstein published his revolutionary theory in 1915, he introduced a new way of looking at gravity, not as a force acting at a distance, but as a curvature of spacetime caused by mass and energy. In simple terms, gravity wasn't something that acted on objects from afar, rather, massive objects like planets, stars, and even light itself were bending the fabric of spacetime, creating what we perceive as gravity. Einstein's theory described how massive objects could warp spacetime, but it was a series of mathematical solutions to his equations that led to the idea of black holes and singularities. The first solution, famously developed by Carl Schwarzschild in the early 20th century, showed that a non-rotating spherical mass could cause spacetime to curve so severely that it would create a boundary beyond which nothing could escape. This is what we call the event horizon of a black hole. But the Schwarzschild solution didn't just describe a black hole, it also described something even more perplexing at its center, a singularity. A singularity, according to Einstein's equations, is a point where the gravitational pull becomes infinite, and the known laws of physics break down. This idea, purely mathematical at first, suggested that at the very core of a black hole, spacetime curves infinitely, and the density of matter becomes infinitely large. This concept would go on to shape our understanding of black holes, but it raised some major questions. If the laws of physics break down inside a black hole, does that mean that time and space themselves cease to function as we understand them? The singularity concept was further developed through the work of Roger Penrose in the 1960s. Penrose's singularity theorem proved that, under certain conditions, the formation of a singularity was inevitable in general relativity. In essence, Penrose showed that if a black hole had an event horizon, a boundary beyond which nothing could escape, it would inevitably contain a singularity at its core. This idea became a central part of our understanding of black holes. It wasn't just a theoretical construct, it was a conclusion based on the framework of general relativity, supported by mathematical rigor. But here's where things start to get really interesting. Not everyone was completely satisfied with this idea. Sure, the mathematics worked out, and Penrose's proof was widely accepted. But the concept of a singularity, the idea that spacetime could be crushed down into a point of infinite density, raised some profound issues. How could something be infinitely dense? How could gravity become infinitely strong? And, perhaps most importantly, how could we reconcile the existence of singularities with quantum mechanics, the other pillar of modern physics? Quantum mechanics is the theory that governs the behavior of particles at the smallest scales, where things get weird. In the quantum world, particles exist in a state of probability, and they can behave in strange, non-intuitive ways. The laws of quantum mechanics work very differently from the smooth and predictable laws of general relativity, and one of the biggest puzzles in modern physics is how to reconcile these two theories. Quantum mechanics doesn't allow for infinities. Everything in the quantum realm is quantized, and there are limits to how small and dense things can become. This is a fundamental problem when we try to apply quantum mechanics to black holes, where general relativity predicts infinite density at the singularity. This contradiction, the clash between general relativity's prediction of singularities and the quantum mechanical insistence on finite values, has been a thorn in the side of physicists for decades. The problem is, we can't test these theories directly. We can't send a probe into the heart of a black hole to see what's really there, and we certainly can't observe the birth of the universe to witness whether it really started from a singularity. So, how do we know that singularities even exist in the first place? And what if they don't? This is where Roy Kerr comes into the picture. Kerr, a mathematician and physicist, is best known for his work on rotating black holes. In 1963, Kerr extended Schwarzschild's solution to include rotating black holes, and his solution, the Kerr metric, has since become a cornerstone of black hole theory. Kerr showed that rotating black holes, unlike their non-rotating counterparts, have two event horizons, an outer event horizon and an inner Cauchy horizon. What's more, Kerr's solution predicted that rotating black holes would not have a point singularity at their center, but rather a ring-shaped singularity. At the time, this was revolutionary. The concept of a ring-shaped singularity seemed to offer an alternative to the traditional view of black holes. But Kerr's work didn't just stop there. Over the years, he has continued to question the idea of singularities in general relativity, suggesting that they may not actually exist at all. According to Kerr, the singularities we've been imagining, points of infinite density and gravity, may be a result of misinterpreting the mathematics, rather than representing a real physical phenomenon. Instead of a point where spacetime breaks down, Kerr suggests that spacetime could have a more complex structure, one that doesn't lead to a singularity. Kerr's ideas have profound implications. If it's true that singularities don't exist, it would mean that the foundation of black hole theory, and even the Big Bang theory, might need to be re-examined. The idea of a singularity at the center of a black hole, and the idea that the universe began from an infinitely dense point, would no longer hold up. Instead, spacetime might not end in a singularity at all. This could resolve the long-standing conflict between general relativity and quantum mechanics, offering a way to unite the two theories into a single framework. So, what does this mean for our understanding of the universe? First, it challenges the idea of the Big Bang as we've known it. The traditional Big Bang theory posits that the universe began as a singularity, an infinitely small and infinitely dense point from which everything expanded. If Kerr's theory is correct, then the Big Bang may not have started from a singularity after all. Instead, the universe could have originated in a completely different way, perhaps involving a more complex, less singular state of spacetime. Moreover, if singularities don't exist in black holes, it could radically change the way we think about the very nature of black holes themselves. Black holes are no longer places where spacetime is crushed into infinite density. Instead, they might represent objects where spacetime has a more complicated, yet still understandable, structure. This could also have implications for our understanding of the event horizon, the boundary beyond which nothing can escape. Without a singularity, the event horizon may be more like a surface of transformation, rather than an impenetrable wall. While Kerr's work is fascinating, it's important to note that these ideas are still speculative. Theoretical physics is full of bold ideas that challenge our understanding, and Kerr's theories have yet to be definitively proven. But the implications of his work are profound. If it turns out that singularities don't exist, we could be on the verge of a major shift in our understanding of the universe. Perhaps we'll finally be able to reconcile the laws of quantum mechanics with the behavior of spacetime on the largest scales. And perhaps, just maybe, the universe will reveal itself to be even stranger and more beautiful than we've ever imagined. But that's not the end of the story. Even if Kerr's theories are confirmed, we are still faced with many unanswered questions. For example, what would the true structure of spacetime inside a black hole look like? How do we unite general relativity with quantum mechanics in a way that makes sense both on the smallest scales and in the vast expanses of the cosmos? These are questions that have driven physicists for decades, and they remain at the heart of some of the most exciting and perplexing research in modern science. One possible solution to this puzzle lies in the realm of quantum gravity. Quantum gravity seeks to describe gravity in terms that are compatible with quantum mechanics, offering a way to understand the force of gravity at the quantum level. There are several competing theories in quantum gravity, including loop quantum gravity and string theory. Loop quantum gravity proposes that spacetime is made up of small, discrete units, while string theory suggests that the fundamental building blocks of the universe are tiny, vibrating strings. Both theories aim to describe the universe in a way that unites the quantum world with the classical world of general relativity. But despite their promise, these theories remain speculative. The search for a theory of quantum gravity is one of the most important and difficult challenges in modern physics. And until we can make sense of how gravity works on both the largest and smallest scales, we may never truly understand the full structure of the universe. As we stand at the threshold of these discoveries, we are reminded of just how much we still have to learn. The universe is a vast and mysterious place, full of puzzles that stretch the limits of human knowledge. But perhaps, just perhaps, we are on the cusp of unraveling some of its deepest secrets. Whether or not Kerr's theories are ultimately proven correct, they highlight the importance of challenging our assumptions and pushing the boundaries of what we know. In the end, the truth about the universe may be even stranger and more awe-inspiring than we can imagine.